Welcome to this presentation on consensus-based distributed multi-target tracking. Due to the availability of modern low-cost sensors, large-scale sensor networks are being used in applications such as wide-area surveillance, disaster response, environmental monitoring, etc. Multiple sensors can cover more area, provide views from different angles, and the fusion of all their measurements may lead to robust scene understanding. Here, we briefly discuss our distributed single and multi-target tracking schemes. Using these schemes in a sensor network, each sensor can come up with the tracks of all the moving targets, without requiring a central server. While distributed estimation schemes have been extensively studied in the multi-agent systems community, they usually require neighboring sensors to have observations of the same target. The novelty of our proposed approach is that this can happen, even if neighboring sensors view different sets of targets. For example, in a network of cameras, each camera has a limited field of view, and may only view a subset of all the targets, at any given time. Suppose there are some targets, for example T1, 2, 3, 4, roaming in an area. A collection of sensors are monitoring the area, where each sensor has a limited field of view. A sensor gets measurements of the targets within its field of view. It may also get some false measurements or clutter. The most important fact to note is that, due to their limited field of views, different sensors are viewing different sets of targets, which also changes with time. A target state consists of some information about it. For example, it may represent the location and velocity of the target in the ground plane. To estimate the target states, the measurements from all the sensors can be fused in a centralized manner. However, one might want to eliminate the use of a centralized processing unit for many reasons, and use a distributed solution where the sensors may be connected using some arbitrary topology. Distributed solutions are more robust to node failure, and scale easily with large number of nodes. Our goal is to track the targets in a distributed manner, using all the measurements in the network. For this, a distributed data association and state estimation framework is necessary. One of the popular distributed algorithms is the average consensus algorithm. It can be adopted to perform various distributed fusion tasks in a sensor network. This is how it works. Suppose each node in an arbitrarily connected network has a state, as exemplified here. The nodes need to compute the average of all these states in a distributed manner. Using average consensus algorithm, each node can update its own state using its immediate neighbor's current states, as can be seen in this video. By doing this iteratively, they all can converge to the average state. The average consensus algorithm is utilized in the different distributed algorithms, discussed later in this presentation. To solve the distributed multi-target tracking problem, we will first consider the estimation of a single target. In a multi-sensor framework, we will also assume that there is no clutter. The optimal centralized tracking results using the centralized Kalman filter is shown here. Here, we will see the tracking results of a consensus-based distributed tracking scheme, known as the Kalman consensus filter, or KCF. KCF was originally designed under the assumption that each sensor can directly observe the target. However, when this assumption is not met, the performance of KCF may deteriorate. This is apparent in the simulation result. For space constraint, we display the estimate of only one sensor. Please note that each sensor maintains its own copy of the state estimate. This state estimate may be different at different nodes. With more consensus iteration per measurement step, the nodes may converge to a consensus. There are two main reasons for the performance deterioration of KCF when sensors have limited field of view. Here, for simplicity, the field of view of only C1, C2, C3 and C4 are shown. The tracking results of C1 are also shown. At first, C2 observes the target and C1 gets information about the target from C2. Later we can see that C1 can neither observe the target, nor can it get information from its neighbor C2 as it is not seen by the neighbor itself. It is as if C1 becomes naive about the target. Another issue here is that the tracking results at each node are highly correlated with each other, and this correlation is not incorporated in the KCF framework. Next, we present the tracking results of our proposed algorithm, the Information-Weighted Consensus Filter or ICF. This algorithm is able to overcome the above-mentioned challenges. ICF uses the average consensus algorithm to fuse the information from different sensors. However, the information from each sensor is weighted optimally by its information content. Due to this information weighting, the performance of ICF is not severely impacted by naivety. This information weighting is performed without any significant increase in communication or computational burden. The cross-correlations between the state estimates of neighboring nodes are also taken into account in ICF. This is achieved by utilizing the fact that consensus is already running, and the state estimates at different nodes are almost equal. This fact is demonstrated here. At each measurement window, after a few iterations, the state estimates at different nodes converge. This video shows how close the ICF estimates are to the ground truth. Each node communicated only twice with its neighbors, after each measurement step. Next, we briefly discuss how ICF works. Suppose, at some point of time, the target state is X. A sensor Ci can observe the target. Ci gets a measurement of the target. Each sensor Ci also maintains a prior state estimate for the target. At each node, the prior and the measurement information are weighted by their covariances and fused together. The covariance of this fused information is also computed. The fused information and its covariance is then combined in a message MI. There are other sensors connected to Ci, which may or may not observe the target. For a node not getting any measurement, only the prior information gets included in the message M. This is due to the appropriate weighting of information. This takes care of the issue with naivety. Each node has its own copy of M, which they share with their immediate network neighbors. Iteratively doing so, using average consensus algorithm, they can compute the average M in a distributed manner. From M average, each node can update the state estimate for each target. Note that the prior information at each node is incorporated in the computation, utilizing the fact that the states at each node has converged due to consensus at the previous time window. By doing so, redundancy in the prior information at different nodes is taken into account. With more communication between the nodes after each measurement step, ICF is guaranteed to asymptotically converge to the optimal centralized estimate, as can be seen from this video. For example, here 20 consensus iterations were used per measurement step, and ICF almost converged to the optimal centralized estimates. Next, we will consider the problem of distributed tracking of multiple targets. We will also consider that some false measurement or clutter may be present. For this, along with the distributed single target tracking scheme, a data association scheme is required to associate the measurements to the tracks. One solution to this problem can be achieved by associating the nearest measurement to each track. And then, ICF can be used for the distributed estimation. However, the simulation results show that this approach is not useful in the presence of clutter. It is because the nearest neighbor data association fails in the presence of clutter. Based on a probabilistic data association scheme and the KCF algorithm, an approach called the JPDA-KCF was proposed. This method works pretty well for multiple targets in the presence of clutter, when all the sensors can directly observe all the targets. However, for sensors with limited field of view, this method cannot be used, as can be seen from the simulation. This is due to the detrimental effects of naivety on the KCF algorithm. Now, we present the tracking results of our proposed method, the multi-target information consensus, also known as the MTIC algorithm. It can be seen from the simulation that the state estimates of MTIC approach the ground truth tracks. Data association in the simulation is performed by using just the position information. Incorporation of other features, for example appearance features, may make the data association very robust when tracks overlap. In this video, the track estimates from all sensors are shown using different colors. The ground truth is shown in black. The track estimate, measurement, clutter and field of view have the same color for a particular sensor. It can be clearly seen that each camera is estimating a trajectory and all trajectories remain accurate even as the trajectory crosses field of view boundaries. Next, we briefly discuss how MTIC works. Suppose, at some point of time, the jth target state is xj. A sensor Ci can observe the target. Ci gets some measurements z1 2 3 4 5, where some measurements may be clutter. In this example, z1 is the true measurement and z2 3 4 5 are clutter. Each sensor Ci also maintains a prior state estimate for each target. For each possible observation target pair, Ci computes the probability that the observation is the true measurement of the target. This is the probabilistic data association step. Using all these information, Ci computes the message Mi containing its current track information. There are other sensors connected to Ci, which may or may not observe the same set of targets. They all have their own copies of M, which they share with their immediate network neighbors. Iteratively doing so, using average consensus algorithm, they can compute the average M in a distributed manner. From M average, each node can update the state estimate for each target. For a single target, and in the absence of clutter, we do not need the data association step and the MTIC algorithm simplifies to the ICF algorithm. Thanks for viewing this presentation. The related papers and implementations are available at the author's website. For any questions, please feel free to contact